Kirchoffs Law, and, well, specifically battery, capacitor, and resistor circuits, as well as capacitor, inductor, and battery circuits, as well as inductor, capacitor circuits. They're able to use Kirchoffs Law to get the charge in the capacitor, all the things going on with the circuit, to be honest, because you can apply it in terms of current and you can apply it in terms of voltage and differences and such. How we're going to start off is going to be with a simple circuit. Simply specifically that. How we're going to set that up is we're going to use our general statement. That's an R. And that's a C. So, Kirchoffs Law, when we're talking about it in terms of voltage, what happens is we have our starting, because we're going in that loop right there, it's going to be starting minus our drop across our resistor, minus our drop across our capacitor. It's all going to be equal to 0 then. Okay, this isn't horribly bad. EMF of battery, just the EMF of the battery. For the resistor, it's just going to be IR. For the capacitor, it's just Q over C. Depending on what level you are in, and how sophisticated you want your discussion to be, you're going to get different values. In this case, I'm going to talk about on the level that AP Physics C, electricity and magnetism, wants to talk about. So we're going to turn this into a first order separable ODE, and we're going to solve it. It won't be bad. It's pretty easy in terms of diff EQs, but you are expected to only kind of touch on the idea of separable ODEs by the time you get to this. So don't feel bad if it is on the more difficult side. It's just when you get more experience, you realize separables are the easier way to go about it. Because we're going to talk about a method of undetermined coefficients later for the inductor capacitor circuit. So what is necessary for us is to recognize that IR is good. However, if we want to solve for Q, we're going to have to get some differential with dQ and dt in it, since we are talking about Q with respect to time. So this is rather easy. You notice that I is going to be dQ dt times R minus Q over C equals 0. How you decide to go about this is kind of up to you. I personally prefer to just start by moving my dt everywhere. So minus 1 over C Q dt equals 0. And then from here, you're going to take everything that's going to have dt and you're going to factor it. So minus, and then we're going to have, oops, we're going to have E minus 1 over C Q dt equals 0. I don't really like having a fraction here, so what I'm going to do is I'm going to multiply the C everywhere. In fact, I'm going to multiply negative C everywhere. So what that does for me is that turns this into a plus, that turns into that. This does become negative, this becomes positive, and it gains a C, and that's it. So what this now is going to turn into is RC dQ, and then we get Q minus EC dt, and I should have included that there, my bad. It's going to be equal to 0. This turns out to be kind of trivial. I hate to say it that way, but what I'm going to do is I'm going to erase this so I can work upwards. And we apply our separation. So what we do is we get RC dQ minus. What I did forget to mention is that now this upper Q is going to become just a lowercase q because these q's are the same. So minus q minus EC dt. We're going to want to get all the q's on one side and anything with t on one side. And I'm going to want to move this RC as well over because that just makes life easier. So what we end up getting is dq over q minus EC equals, and then all we have is going to be dt over RC. This is, again, still pretty easy. What we're going to have to make the connection for is that we're going to integrate from zero charge in the capacitor to total charge in the capacitor, which is an uppercase Q. And with respect to time, we're going from 0 to t, which is our variable. So I'm going to do a capital T only because we have t right there, and I don't want it to be confusing. So this is easier. This is just going to be ln q minus EC eval from 0 to capital Q equals, and then this is simply just going to be T over RC minus 0 over RC, which is just T over RC. We take over here. We have this. We're going to apply our log rules, and what that will get us is Q minus EC over minus EC. And this overall is just going to simplify to ln 1 minus Q over EC equals T over RC. Okay, we have T over RC. Then we do one more move, and what we get is 1 minus Q over EC equals e to the T over RC, which overall is going to imply that EC1 minus, I think so, right? Boom, boom, yeah. E to the negative T over RC. Okay. I didn't do anything. Oh yeah, so I did miss a negative. Little mistake, my bad. So that negative does carry through everything, and that ends up right there. And that is going to be equal to Q with respect to time, and that negative mistake happened earlier when I was bringing the negative C throughout everything. I just forgot to put it on the side, on the stuff with the DT. So, honest mistake right there. And that's how you derive that. This is the easier of the two, though. And do look at that equation and analyze kind of what it means for the time of the circuit. What you should notice that means as our capacitor fully charges over time, slowly that happens, and also is going to indicate that in the end, as Q approaches E, well, technically EC, but the EMF that is going to be produced by it is going to then eventually just equal it to E, which is the EMF of the battery. It's going to mean that it's just going to stop all current. Now, the main circuit, which I don't like. We have our battery, an inductor, a capacitor, and that's it. So we get L, my bad, C, and of course E right there. We're going to set up our loop. E minus I dropped that inductor's going to cause minus, I'm just going to put a Q over C because we did that last time. This is weird because what this is going to be equal to is going to be negative L di dt. Okay. So what one's going to have to realize is that if dq dt equals I, then di dt is going to be the second derivative of q with respect to t. T. So there, we're going to plug it in, and we get the second of q with respect to t. Not fun. And there is unfortunately no way to make this nicer. But the way that you would solve it is you have to recognize a certain form, and that's going to be, it's a non-homogeneous second order differential equation. And so what we have is LQ double dot minus Q over C equals negative epsilon, which is our battery EMF. This should look similar to a form that is C1 y double dot plus C2, which is 0 in this case, y dot plus C3y equals some constant. Not fun. But what we realize for this equation is that our solution is going to be in the form of C1 e to the lambda t plus C2 e to the lambda t. And that is our solution general and our solution particular. That is a differential equation topic. I'm not prepared to talk about it today. I may in the future, however, but undetermined coefficients is the method that is needed for this. That is what is needed. So, if you find yourself prepared to solve this equation, by all means go ahead and solve it. Maybe you can apply the one with the L. I forget its name. I always think of Lagrange when I go to it. The Laplace. Maybe you can use the Laplace transform to do it. As said, I haven't done a lot of diffie-qs, only enough to know and talk about them. So, maybe once I get work on the Laplacian, I can do this, but for now, unfortunately we can't. And I don't know why I said Laplacian, it's the Laplace transform. Thank you, and any questions I do always appreciate. Thanks.